Okay, so today's lesson is relative motion. And I think one of the easiest ways to think about this is when you're riding on the bus or the LRT, and you get up and you start walking while on the already moving object. Okay? So if I'm on the LRT and the LRT is cruising on an eastward velocity, and the LRT is moving and I'm sitting here, you can look out the window, you can see that you're moving. You are on the LRT, you have the speed of the LRT. Now if you get up on that LRT and you start walking around like this, to you feel like you're going your normal speed. Maybe it's like 1 meter per second. However, to somebody outside the train who's watching you, you have a relative speed. You have the speed of the LRT plus your speed. It combines like that. So relative motion, we are going to be talking about what it would look like to an outside observer. So objects or object, anything like this, moving in a medium. So when I talk about a medium, I'm talking about like a plane in the air or a boat on the water. The medium is the air or the water. So object moving in a medium with respect to an like outside observer. So somebody who's not, in the inertial state, if you will. So an example would be if you're on an airplane, or if you're on an airplane, the medium would be the wind and the observer would be on the ground. Okay. And I'll highlight this so it's clear. The plane is the object. The wind is the medium. And then the outside observer is just like a person on the ground. So imagine like you're trying to think about how your plane is going to get to another destination. Like if you head on a certain path, and that's the velocity vector, if you take a certain vector, what if there's a wind? The wind is going to change your course. Do you guys agree with that? Does anybody play golf? If it's a really windy day and I wind up and I smack that ball, then what's the wind going to do? Even like when you're playing football, a lot of you guys are on football, right? So if I want to throw it to Kane over there and I throw the football to him, but the wind is heading that way, like that ball is going to take off because of the wind. Okay, so this is what we're talking about, relative motion. All right, some more notes and then we'll get into some of the physics. That's a little bit different. That's a little bit different, yeah. That's a little bit different. That's something else. That's not the centripetal. Something else, yeah. Yeah, exactly. So just copy it down and then I'll explain it. So I'll copy this down and then I will explain it. And I think I've already explained it. But all it's saying is that the magnitude of the velocity of the moving object with respect to the observer will not be the same as the speedometer on the object. So this is like completely bogus, but imagine you're driving your car. On the car you see a speedometer, right? Imagine, you know, the car was on a treadmill and the treadmill had some motion as well. The actual speed that you have is not going to be the speed that's on the car. Does that make sense? The motion is relative to the outside observer. So while you're driving the car on the treadmill, you think you're going, say, 60 kilometers an hour. But if the treadmill is going like reverse, 20 kilometers, the outside observer notices the difference. You're actually only going 40, whereas you think you're going 60. So this is called relativity. Motion is relative to the observer. And usually the observer is some stationary person outside the event watching it. Okay? So we can get into some very basic examples with a plane and the wind. So let's call this a tailwind. So a tailwind, and I'll just draw the plane as a box. Okay? Let's say the plane has a velocity, we'll call it v2. The plane has a velocity of 100 kilometers an hour to the right. So the plane has some velocity. And I'll draw that vector a little bit better. Okay, so there's the vector v2 for the plane. And let's say you're experiencing a tailwind, so the wind is behind you, it's with you, so it's in the same direction. And I'll just put it behind and a little bit smaller. And we'll call it v1, and we'll say it's 25 kilometers an hour. And we'll call this a tailwind. What do you notice about the vectors? They are in the same direction. So when we add them, we just have to keep them the same sign. If they're in the same direction, they have the same sign. Okay, so in this case, when we add them, and we call this the result, the resultant vector, it will be 125 kilometers per hour. Right? So if I hit a golf ball and the wind is behind me, I'm going to get extra distance. If I throw a football in the air and the wind is behind me, I'm going to get extra distance. And I think that makes sense. When you add vectors, you combine them like this. If they're in the same direction, they add up. And so, you know, similarly, you have your headwind. You're going to have the exact same numbers. Okay, so I'll just do this in blue. It's the exact same picture. You have the V2 is still 100 kilometers an hour, this plane. Sort of just a made-up number, just easy numbers for us to work with. But we'll say it's a headwind, so it's in the opposite direction. So V1 will be negative 25 kilometers an hour. And the negative is there just to show you that it's in the opposite direction. And when you combine these ones, the resultant vector is 75. Of course, when you fly into the wind, or if you throw a ball into the wind, you know, it's going to slow down. You're going to get less distance out of it. So the resultant velocity is lower. Because when you add vectors in opposite direction, you have to be mindful of the sign. And when you add them, one is positive, one is negative, and the result is less. You guys okay with that? Okay, this is a Science 10 sort of demo with displacement. Do you guys remember doing this in displacement? Well, it's no different with velocity. Velocity is a vector. You treat it like a displacement vector. Everything's sort of the same with it. It's just a different unit and a different idea. Okay? Now, in the physics 20, we're going to put them at right angles for the most part. You know, in physics 30, it could be any angle, usually. In physics 20, I'll show it to you, any angle. But for the most part in physics 20, it's always going to be a right angle, so we'll do basic trig. Okay, but in physics 30, it could be any angle, and I'll show you how to do that as well. Okay, so let's do the side wind. Any questions so far? Okay, let's do the side wind. And I'll just do it a little bit differently, but it's pretty much the same. So we have the plane velocity, velocity of the plane, plus the wind velocity. And this is what we were doing on the last page as well. And this will equal the resultant velocity. Okay, and with the side wind, we are going to assume that it's perpendicular, so they're at 90 degrees to each other, and then we can do basic trig. Okay, so let's say the plane's velocity is same idea. V2 is 100 kilometers an hour, positive. And the wind velocity, so I'll just draw in that vector for you, plus the wind velocity, and we'll call this one negative 25 kilometers an hour, but it's headed south. Draw it a bit better. And the negative, like, I wish I'll just put 25 south, you know, it's the same. So how can we do the result? Call this VR. And I'll just blow this up down here below. Yeah, and you just do your basic trig on this. So if the plane is flying east and the wind is pushing you south, you'll end up with a resulting velocity that's south of east. You'll end up south of east. I'll draw in the two components. This is your 100. This is your 25. And we're looking for the result, R. R is very easy to calculate. It's just going to be Pythagorean theorem, 100 squared plus 25 squared. And theta is also going to be very easy to calculate. It's just going to be the inverse tangent of the opposite over the adjacent. So please, I'm just going to demo this on the calculator to just really show you how easy this is. I did this for Joel today, and he's like, oh, you're so smart. And I'm like, no, man, it's just that easy. And this, again, I'm not trying to make this seem easy, but I'm just trying to show you that this can be done very quickly. And I'll put that back up in a second. But please watch on the calculator. If you start the square root like this, and you put in the two components, the x component and the y component, and the sign is not important, just the numbers, because this is the magnitude right now. I got 103. And then second function tangent of the opposite divided by the adjacent. And I'm not in degree mode, so that would help if I was in degree mode. And I'll do that again. And I got 14. See how easy that can be? One step for the Pythagoras, one step for the angle. Please memorize that process. You're going to need it in 30 as well. And then when we get into the force diagrams in the next unit, you'll need it then as well. Okay, so we have, I apologize, was this 103? Yes. And I'm not worried too much about sig digs right now, just for the notes. And this one was what angle? 14, rounded down is 14? Okay. All right. So let's communicate this velocity vector properly. The magnitude is 103 and the unit is kilometers per hour. There's the magnitude. Vectors always have magnitude and direction. The direction is, of course, 14 degrees. And you look at this angle, it is south of the eastern horizon. So we write south of east. You can stick with those Cartesian coordinates. people taking 20-1, you're going to learn those RCS coordinates in that course. So you're going to be okay. And I'm not going to test you on RCS anymore, other than that quiz. Okay? It'll be strictly this Cartesian reference, cardinal reference, or whatever they call it. Okay, any questions so far? This is sort of stuff we already know. Okay? So let's try some harder stuff. This is the riverboat problem. Very typical of a first-year physics course, riverboat problem. Okay, so we need to draw a picture of a boat on a river, and we're going to have to draw a person on the shore, sort of watching this happen. So draw a rectangle. Okay, draw a rectangle, and draw in a couple lines just to demonstrate that this is the shore. And I'll color the shore green. This is just the shore. Somebody is outside what's actually happening. He's outside the medium. The medium is in here. What is this? This is the river. Fred is not in the river. He's on the shore, safe. Okay? He is the observer. In the river is a boat. The boat is crossing. However, there is a current. So I drew those lines. I'll draw those lines vertically so you can like tell that there's a current. So we'll go like this. Okay, so those are the current lines, if you will. And here's this boat. So the boat is trying to get across. But what's going to happen to the boat? Just make a prediction. Is it going to get straight across? It's going to head. The boat thinks it's going to go straight across. And that's important to note. You're on the boat. You're not Fred. You're on the boat. You think you're going straight across. But Fred watches something else. Fred watches as you traverse. This is happening to the boat. Fred notices that, but the person on the boat does not. That's a relative motion. Okay, so you notice that the x component of the boat, like that's the velocity heading of the boat, but there's this current pushing it upwards. So the result is this path taken like this. And it's very similar to what you're used to. Okay, so let's just jot some notes about this situation. The current influences the motion of the boat and carries it downstream. So just get that down, and then I will show you what I mean by downstream. So that highlighted in purple next to the observer, that's what I mean by downstream. You thought you were going to go across, but you actually got pushed down the stream a bit. Even though the boat thinks it's going straight across in the eastern direction. But because of the northern velocity of the stream, you're pushed north of east. You guys see that? And the opposite side of the triangle would be that downstream, what they're mentioning by downstream. Okay, we have the resultant, the velocity, the resultant velocity magnitude is greater than the boat's. And at, yeah. Let's just and the direction is at an angle rather than straight across. Okay. Is there any questions so far about this riverboat situation? Are you guys you understand this scenario? So the velocity vectors are, and in real life, like if I throw a football up in the air, the wind has like so many different vectors up there. It's not like a constant stream. There's infinitely amount of vectors happening, and so like it's really hard to actually figure this out. Even on the river, like there might be like an average velocity, but there's all types of currents happening. Yeah. Yeah, of course, yeah. Upward currents, yeah. Yeah, exactly. There's infinite amount of currents going on, completely random and chaotic. We're just trying to really boil it down to some simple ideas here. And it's important for us to understand physics in the components and how they affect the result. Okay, so let's keep this going. Let's make another page. Okay, so let's analyze what's happening here. We have a tip to tail. You guys remember this? Tip to tail vector diagram. Okay, you have this velocity of the boat, which was east, so you could call that like V boat if you wanted. And then there was this northerly current. You could call that V current. And then we'll use Fred as an example one last time. What does Fred see? And I'm on the boat. If I'm on the boat, Mr. Line number's on the boat, what does he experience? What do I experience? Motion sickness? What do I think I'm doing? Yeah, I think I'm V boat. What does Fred see? The resultant, yeah. He sees me go off on this angle here. So this is remember Fred was the observer. He sees the result. Okay. So let's put in some numbers, some easy numbers to work with. We'll call the velocity of the boat 4 meters per second in the eastern direction. And the velocity of the current, we'll call it 3 meters per second. Just for easy numbers. And this is in the northerly direction. So you guys know this triangle, 3, 4, 5 triangle. So you do a little Pythagoras and you get the result. So VR is 5. You guys okay with that? Little Pythagoras? And then to find the angle, second function tangent of 3 divided by 4. Okay, someone do that for me quickly. Second function tangent 3 over 4. 37? And Habibo, I'm putting you on the spot, okay? You got this. Don't help her, you guys. What direction is this 37? North of? Yes, Habibo, you got this. North of east. Okay. Now, let's see what kind of questions you're going to get with the riverboat problem. The first question you'll always usually get is, what is R? What is the result? Okay, and we just did that, so pretty straightforward. Now, the second question that they usually give you is like, if the width of the river is x wide, how much time to cross the river? Okay, pretty straightforward. If the river is this much distance, how long would it take to get across? And then the other question that they'll ask is, what distance downstream does the boat reach on the other side? And remember, I highlighted downstream on the previous page? It was like you thought you're going across, but you actually got pushed. So it's like, how much did you get pushed? What distance downstream does the boat reach? Okay, so we're almost done. Let's just answer. We already did B and we already did A. Do you guys remember we did A just above here? Look above for A. What is R? Well, it's just a little Pythagoras. We've been doing that for a while, and some tangent. So let's answer B and C. Let's give you a second to copy this. Okay, so for both questions, for B and C, you're going to use your average speed equations. Because the current is perpendicular to the boat's motion, it doesn't affect speed. Okay, so because the motion of the current is perpendicular to the motion of the boat, okay, it doesn't affect the left-right velocity. So, like, you just use these average speed. There's no acceleration going on. You just use these average speed equations. There's no acceleration. So all that stuff in quotation is basically no acceleration. Okay, so for B, we're looking for the time. And time, if you rearrange it, time is equal to D over V average. And let's go back to that original diagram. Guys, go back to this diagram. And we'll say that the width of the river X, let's just make it an easy number. Let's call it 80 meters. They say the width of the river is 80 meters. And what direction is this 80? Is it left, right? Is it up, down? This distance 80. Is it left, right, or is it up, down? Left, right. So this is an x distance. So I just put a little here, x distance. Because it's in the horizontal component. So this is where it gets quite interesting with the physics. Which velocity do I use? Which velocity do I use? Whoops. We know the distance across is 80. So think about this. Do I use VR? Do I use V boat? Or do I use V current? Which one do I use? But if you use VR, you would have to use the distance of the hypotenuse. Yeah. So this distance of 80 meters is left and right only, right? So you have to use the velocity of the boat, which is Vx. So I'm going to call that Vx, and I'm going to put a little circle around it, and I'm going to put, this is the boat. So the time it takes to go across for the boat. Yes, sir? Oh, zoom out a bit. And what was the velocity of the boat? The velocity of the boat was 4, right? Okay, so the meters cancels, the seconds come up top, and you get 20. 20 seconds to go across. Any questions on that? That's so key. Put a big star on there. You have to know that. You have to use the dimension. The dimensions have to line up, so to speak. Okay, if you're going to use 80 here, you got to use the velocity that's in that direction. Okay, so C was the distance downstream. So now we're solving for D. D equals V average times T, so VT. Okay. Now this distance that we are searching for downstream, go back to the picture. This is this distance I highlighted purple. What distance is that? Is it left, right, or is it up, down? It's up, down. So we call this like a y distance, or a y component, if you will. This is a y distance. And we're trying to find that. Okay? So that downstream amount. Okay, so what I'm going to do is I'm going to put this actually dy, and I'll do that on the next step. Dy is equal to V average in the y times time. Okay, and what is the average velocity in the y? It's the velocity of the current. So that's going to be 3 meters per second. And I'll put a little note on this. This is the current. And what time do we use? Do we use the 20 seconds, or is it a different time? Well, I wrote it, so it's probably that one. So why is it 20? Back to the picture. Use my pointer. So with the velocity heading east, in the time with the velocity and the distance, it took 20 seconds to get across. In that same amount of time, the y velocity has pushed you a certain amount of y distance. So the times have to be the same. Whatever happens in the 20 seconds in the x is going to happen in the 20 seconds in the y, and you get this result here. Okay, so the time is going to stay the same for both dimensions. Time is consistent. And I could put that as a note as well. Time is consistent. Okay, and then you get 3 times 20, the seconds cancel, and you get 60 meters. Okay, so the math is not difficult, you guys, and I think everyone is noticing this. The math is not difficult. You're rearranging VDT in Science 10. So the math is not an issue. It's the physical, conceptualization. So it's the conceptual that's hard. Conceptual is hard. In the sense, which vector do I use? Which vector do I use? Okay. So this is a good question to study. All right. So got about some time for the homework. If you look at page 120, and there are some workbook questions, ranging in difficulty, of course. So I'll put it down here, workbook. Oh my gosh. Workbook, page 120, and it looks like 1 to 7. Okay? And again, ranging in difficulty. Progressively getting harder around 6 and 7. So if you're that type of kid that only gets the first few questions done and then forgets about it and needs reminders to do stuff, then it's going to suck. You're not going to, really reach your excellence. Okay? So really try to push yourself to get to 6 and 7. And we can go over some of these questions tomorrow. But please don't do nothing and then come in here tomorrow just expecting me to do these for you. Okay? Don't do that. Okay? So I feel like we'll do a relative motion quiz on Thursday. That way I'm not giving you quizzes to redo. Give you one extra day to prepare.